Welcome. My name is Scott Elrod, and I am the Associate Director at the Stanford Office of Technology Licensing. This is the first in a series of Stanford Inventor webinars, and we're really pleased today to bring to you technology from the lab of Professor Pierre Kiriakou. It's ultrasonic devices for capture of touch on touch screens. Pierre himself is not able to be with us this morning because of a family situation, but we're fortunate to have with us Kamar Feruzi, who is a co-inventor on this invention. Kamar received his PhD degree here at Stanford University in the Department of Mechanical Engineering, and he did his research in Professor Kiriakou's lab. So maybe you could just tell us a little bit about what the Pierre Kiriakou group does here at Stanford. What's the focus of the research?
Sure. Professor Kiriakou is an electrical engineering professor at Stanford University, and he has been pioneering the so-called transducer technology, ultrasonic transducer technology called capacitive Markov-Mission ultrasonic transducers, also known as CMOS. And in addition to that, we have been working on basically transducer technologies and also in general ultrasonics for different applications, including industrial applications, also medical applications, and yeah.
Great. All right. Well, maybe you could dive into the technical details now. And what I'll tell the audience is that he's going to present for about 15 minutes. Then we'll have a Q&A session. So when you enter a question, we'd ask you to use the chat function. On the Zoom window, you'll see, if you mouse over the window, you'll see that there are two options. You could use the Q&A function, or you could use the chat function. And it turns out to work better if people will use the chat function. So with that, I'll turn it over to you and look forward to hearing your talk.
Okay. So the subject of our invention that I would like to basically explain is multi-touch ultrasonic touch screen and also gesture sensing, which is basically sensing the touch at a distance from the screen.
Or not working. Says that the brother
share screen.
Mm-hmm. Go ahead.
Okay, so so in the first part of the talk, I will go through the main key points in terms of applications and motivate basically the problems, the problem we're trying to solve and what exists in the market. So I think it's needless to basically emphasize the touchscreen technologies in a lot of applications, diverse applications, many different fields, including, as you can see on the screen, from medical side to the entertainment to banking, finance, and whatnot. And they basically form a big market. And if you look at some of the graphs on the screen, you will see that basically generate a lot of revenues, and basically they are sold billions of units each year. And of course, there are many technologies on the market, but the mainstream ones are known as capacitive ones, where you basically have capacitors basically patterned underneath the screen to basically sense the touch. And the resistive one is the old one, and the ultrasound one, and optical one. And looking into touch technologies, basically the key feature that all of these technologies basically aspire to address are manufacturing costs, integration costs, which is the most important one, and also the hardware complexity, hardware architecture, power consumption, and optical performance, plus some other factors. But if you look at the market, really, ultrasound one, which has a lot of advantages over the conventional one, like the capacitive ones, resistive ones, which I'm going to basically motivate in the next slide. If you look at the market, given all those advantages, ultrasound shares less than percent of the market. And that was like the motivation for what we tried to do. And I would like to draw your attention also to the paper that was cited there by G. Walker, and which goes through all the details that I motivated just now. So, as a refresher, ultrasound is a high frequency mechanical waves, typically more than greater than 20 kilohertz. Ultrasound offers a lot of advantages, including high optical performance, generally because the sensors are integrated on the perimeter of the screen rather than being patterned under the screen. It can be sensitive to any object, including finger, gloved hand, stylus, and whatever that can interact with the ultrasound waves. It had a very simple structure, at least the new ones, new technologies, and most importantly, it is very inexpensive, the cost of manufacturing. There are many commercial technologies out there these days, but conventionally, probably the most dominant ones are the surface acoustic wave, which goes back to 20 years ago or more, where basically the sensing is done by the so-called surface waves or the Rayleigh waves, and the other recent technology of acoustic pulse recognition for dispersive signal technology, where basically they utilize the so-called bending waves or the fluctual waves. And these technologies offer basically a great deal of advantages. However, they are still lacking some key points, including that they can't really provide a multi-touch. They can provide a touch and hold because, for example, acoustic pulse technology works in this way that you have to tap the screen. Once you tap it, you generate the wave. The wave will propagate to the edges and are picked up by the sensors. However, this is not capable of giving you a touch and hold, simply because once you tap it, the waves will gone. You can't really sense the hold part. And they generally lack robustness because of the sensitivity of ultrasound waves, and they provide poor touch sensitivity. And of course, the high activation force because of the tapping effect that I just motivated. So the problem we're trying to solve, our invention basically attempts to solve these problems. First of all, as I mentioned, the main advantage of ultrasound is the simple structure, simple architecture, and also inexpensive manufacturing. So for that, that's one of the key objectives that we try to address, where we basically try to limit the spatial measurements. Because generally speaking, the cost of the manufacturing scales with the number of spatial measurements you have. Like for example, for a capacitive one, also hardware complexity. Like a capacitive one versus the ultrasonic one. So in this technology, we try to utilize physics in an intelligent way, or smart way, to basically limit the number of measurements we have. And we claim that we can basically use one or only two sensors to basically sense a touch. Also, we wanted to improve the touch sensitivity and improve on the robustness of our technology. And I'm going to explain in the details of the technology that if you are smart in choosing the proper waves, ultrasonic waves, we should be able to do that. And we do it through what is called the guided waves in a screen. And also, we would like to have a multi-touch capability, which is not robustly on the market yet. And for that, we basically work on a signal processing technique that basically can provide that feature. The other technology we've been working on is gesture sensing. First of all, I want to motivate why ultrasound imaging in air is unhelpful as opposed to, for example, the optical imaging. As you can see, there are many key features to that. As you can see on the screen, you can basically, the application of ultrasound imaging in air include gesture sensing, face recognition, 3D mapping, and whatnot. It's immune to the light variation because it's simply mechanical wave propagation. You don't have any electromagnetic radiation, no moving parts. It generally comes with low power consumption, and is omnidirectional. And in the bottom, you can see some certain applications of ultrasound imaging in air. For example, potential applications like the gesture sensing, as you can see, and also the one on the left, which basically measures the distance from a robot, where you basically say something about the topography of the ground. And I would like to draw your attention right now to a technology that our lab has been developing during last few years, and that's a specific CMOD technology, which we call CMOD indented cavity. And the advantage of this technology is that yours is specifically designed for airborne applications, and we basically design them in a way to come with tunable sensitivity and bandwidth, which is sort of hard to balance when you're doing imaging in the air. And they provide better image resolution, high frame rate, and basically you can use the same transducer to receive and transmit. So with that, I would like to basically dive into the technical details and describe more how basically it works and how we do it at Stanford right now. So this is just an overview of the same slides I presented. So getting into the physics, I'd like to start with physics of the touch screen and the way we basically improve the robustness. We do it through the so-called land waves or the guided waves inside a plate, which are basically the waves getting propagated into like a very thin slab of material. And they are advantageous because they can be very sensitive to interaction with the medium on the top and the medium on the bottom. And also they provide, they don't have as much attenuation as the bulk waves. And they are used in industry, especially in under-circuit testing for basically evaluating the samples and components of a mechanical system. One other advantage they have that we try to utilize is that they can leak, meaning that if you put them in immediate neighborhood of a dense medium such as human finger or water, they can leak energy, and you can think of it as a mechanism that a touch or a human finger can interact with the ground waves. The other feature we try to utilize that helps a lot with reducing the number of spatial measurements and thus the cost of manufacturing and improving the hardware complexity is the reverberant field, or reverberant field coming from the land wave. And what it means is that I'd like to show you a very brief example of what it means. So when you have a propagation in a bounded structure, such as a plate with boundaries, in the beginning of the wave propagation, the wave structure is very coherent, and that's how people use the wave imaging in classical imaging setting. However, once the waves start bouncing off the boundaries, you end up with a complete chaos, as you see on the screen. And that chaos indicates that the energy is distributed all over the place. And what it motivates is that you can basically ensure, if you limit the number of spatial measurements, you can ensure that you can say temporally what is going on inside the domain. Meaning that if you listen to the echoes that are coming only in one transducer, it captures all the information, all the spatial information you're missing by limiting your spatial measurements. So simply speaking and putting like in summary, this is what we do. So we have a screen, we integrated with the small transducers, limited number of them. We transmit one of them, receive with the other one, and we look at how the touch basically affects the signal. And because of the reverberation, that single measurement is enough to basically say where the touch is. This is a sample prototype that we built in the lab, where we have a screen, as you can see on the screen. There's a glass screen. Underneath the screen, there are some grooves basically for the guidance to the algorithm, which I'm going to present in a minute. It's not required. This is just a lab prototype. But simply speaking, it is a screen integrated with a screen or piezoelectric transducer, a small cuboidal piezoelectric transducer you see on the screen. And if you look at the dimension, it's like a tablet-sized screen with 10 inches times 6 inches times almost 1 millimeter basically thickness. And the cuboidal element is basically a small 1 millimeter roughly times 1 millimeter times 1 millimeter piezoelectric transistor, which are bonded to the screen. We studied physics of the system. This is basically like a simulation that shows actually what happens as the waves propagate and interact with the touch. And on the right, you will see basically how a touch basically affects the whole signal. We basically utilize this simulation to understand the physics better and basically come up with the algorithm, which I'm going to present next. So now, of course, the main part, the million-dollar question is, once you have this chaotic information, how do you process? How do you say where the finger is? And this is basically one of the key features of what we have been doing. And that's basically using machine learning. We have tried many different algorithms including all the machine learning ones and classical imaging techniques. And this one appeared to work robustly for many, many, many touch points. So basically the way we do it, you basically train the plate in the sense that you go in the training phase, you divide the whole process into two steps. In the first step, you go over the plate, you do the training over the screen, and in the second step, you come back and you do localization. And the way you do the training, I would like to emphasize is that you use an artificial finger, or a phantom, as we call, and then you go over the screen using a single touch and record training points. And the next step, you come back, you touch it with multi-touch, and you say where the touches are. So, but of course, we have to make a comparison between what is existing out there. And one thing I forgot is that there's a paper in the Journal of Physical Society of America on the whole machine learning technique that they utilized, and also there is a paper which you can see on this slide that basically reflects on the whole technology in detail, which we published in IEEE transaction. So getting to the comparison between the existing methods. So there are certain techniques out there. They are called correlation method and Manhattan method. And here what we did basically we tested them on our sample for our prototype with 1 touch and 3 touches. And as you can see here for the 1 touch, one of them really barely works. The other one, I can't really tell it works. For the multi-touch, apparently, basically, as it's evident, none of them actually work. Now, instead of basically showing you 1 touch or 3 touches, I'm going to show you many, many touches, including up to 12 touch points on that tablet size. As you can see here, we have a decent improvement over the existing methods that can clearly distinguish many, many, many touch points. And the other problem we also solved, which is a big problem, I would say, in ultrasonic technologies, especially in the frequency that we are working with, is the noise. Noise that is coming from the mechanical noise or thermal noise. For example, you put this screen under the sun. You can go to some countries. This can be anywhere from very, very cold temperature to very, very high temperature. This emulates, for example, as you can see, is about 42 degrees C. For example, we in California, like last 2 weeks, we experienced this temperature. As you can see, it can basically increase the temperature of the plate decently, which can alter the propagation characteristics of the long waves or the guided waves. Or you can imagine that basically this screen is integrated with a lot of ASICs and electronics, and they basically heat up, and so the temperature for the screen is not uniform. The question is, how would it alter the signal you measure, and how would it alter the localization? And the results on the top you see, it will make a difference. However, with the noise compensation techniques we studied, you can see we can recover them very, very well. So at the end, I would like to also elaborate a little bit more on the gesture sensing. This is the slide that I motivated by the advantages of the CMOD vented cavity. And here is the platform that we have right now in the lab for gesture sensing. So basically, we have a programmable system called Cephasonics, and we have integrated that with the FPGA, CMOS with the FPGA, and the proper electronics, including ASICs. And we program it, and the demo on the right will show a video that basically shows, as the student basically alters that box, you will see on the screen that how basically our CMOS are capable of sensing or imaging where it is in the air. And I would like to emphasize that distance is over 10 centimeters. With that, I would like to thank you for your attention, and I would be glad to take questions.
That's one more.
Oh. So what I want to say first, this is Scott speaking. These two technologies are both available for licensing. We have a very robust program of licensing here at Stanford. We license to both small companies, startups, as well as larger companies. For anybody who's interested in knowing more technical information about these technologies or talking about licensing, I would ask you to contact the licensing associate for these technologies. That's Evan Elder, Evan, E-V-A-N .elder, E-L-D-E-R, at stanford.edu. And with that, we'd like to open this up for questions. And we're going to, as I asked people to use the chat the chat function, we will look at the questions coming in. So the first one is, good question. May I know how mature is the technology? What is the closest application for these technologies? Can you elaborate the medical application? So there are really three questions there. Maybe you could start with the question of how mature it is.
So I have the whole touch technology was the subject of my thesis, and I would say it's pretty mature at this point. And it's up to the point that it can be given to a company to basically make it into a product. The second question?
The second question was, what's the closest application? What do you think could be the near-term application for this?
Smartphones, tablets, that was like the primary application we had in mind when we were developing that. But certainly, we can have more specific applications. On the medical side, that's a very good question. And honestly, I haven't really thought about it, but I think the potential application would be mainly on the screen.
Mainly for the touch screens.
Mainly touch screens.
I have one comment coming in. It's a little bit hard to hear, so maybe you could speak up a bit.
Sure.
Any other questions from our audience online? Okay, here's another one. Can the technology determine the pressure of the touch interaction?
That's another feature that we are working on. As it stands right now, we haven't basically fully developed that feature, but potentially, yes, it can be used and we're working on it. But that stage is not mature yet. And I'm hoping my voice is now louder.
Great, thank you. Any other questions? Yeah, here's one. How many years is it to massive industry commercialization?
To be honest, I'm a little hesitant to basically comment on that because I'm not a product development engineer. Right, so I can't really give a number on that, but I would say maybe a year or so.
Yeah, I think I would just add that all of the components that would go into this are commercially available. The
Exactly.
piezoelectric elements are really very inexpensive, trivial to attach to a glass plate. And the algorithms, obviously, that's a software or hardware accelerated thing, which presumably for a commercial product, one might want to turn an ASIC to do that. But really, it seems like to me, it seems like a set of engineering tasks as opposed to any fundamental research. Would you agree with that?
Yes.
Great. What is the patent status?
I think that's the question you should ask Mr. Evan Elder.
Okay, well, Evan Elder will be happy to communicate with anybody who is interested in that. We do have patents pending. We aggressively go after and protect intellectual property here, and that's one of the key things we offer to licensees. Another question, is there a fundamental limitation to how thin the transmitter-receiver layer can be? So I guess they're saying that the piezo elements, if you wanted to put this in a very, very thin package, how thin could that be?
So that is determined by the whole design of the so-called guided waves that I explored. So one key feature, for example, is that if your screen is too big and your frequency is too high for that, and basically can't really set up the reverberant field, then it won't work. However, theoretically there is no limitation on how thin the transistor can be because there is always some guided waves that it can excite. The whole premise is to basically I would say trick is to design them in a way that you get the line waves you want or the guided waves you want.
Another question, how high a resolution can you achieve with the technology?
So that's a very good question in terms of the physics of it. Because of this chaos that we have, this resolution is soft diffraction resolution. So basically in classical imaging, we get a refraction resolution, which is the half a wavelength or so. However, in this technology, because this interrogation is at the statistical level, with very, very, very fine fluctuation in state on multiple scales, that can be very, very tiny, or like less than a millimeter even.
And there's a related question here. What minimum resolution between two fingers did you test on the platform? How close could the touches be to one another?
So this is dependent on how you do the training, because putting in a simple set of words, I would say, so if you train it with higher resolution, that will determine how close your fingers can be. So if you need more resolution, you have to train it with higher resolution. So basically, the closest those fingers can be together is the closest two training points can be with respect to each other.
I have, I think, a related question myself. So when you do the training, do you have to train at each of the physical points on the screen that you want to be able to discern later, or can
Yes.
you do?
Yes.
So if
But there is no limitation, please, diffraction limitation on how close they can be.
And so in production, if you were to do testing, or if you get these things set up with the right algorithm, is it reasonable to assume that if the plate is the same size, the piezoelectrics are mounted the same way, that the identical algorithm would be able to discern touch points, or would you have to do a calibration step for each and every plate?
No, I would say no. It can be done on a single plate. So it's a function of the plate. And actually, that's a very good point. So there could be some drift from a plate to a plate because of manufacturing variations and whatnot, and that can be compensated exactly through the same algorithm I presented at the end, because you can really think of it as a mechanical noise over the baseline.
Mm-hmm.
So it can be recalibrated, but the recalibration process is way it's way cheaper in terms of the cost, computational cost, and algorithmic cost compared to the training step. So training step is something you do once on a plate, but the calibration is something that you can do more and more because it's a lot more cost-effective computation.
A couple other questions around the training. What is the size of the trained neural network?
So we are not utilizing a neural network. That's why I refer you to the paper that was listed on the screen. It's a handcrafted machine learning algorithm. We tried neural network. We tried the support vector machine. We tried the different classification regression algorithms in classical machine learning. And also we utilized classical imaging techniques like sparse imaging or beamforming and things like that. But basically this algorithm was handcrafted because none of those technologies actually work. So we are not using any kind of neural network.
Okay, and the last question, we've got 1 more minute. How robust is the training to new users?
So I would say it's very robust, but as I mentioned before, there could be some drift, but the drift can be compensated through the compensation algorithm. And the compensation algorithm costs 1/100th of the amount of data you need to process for the training stage. All right, well, Kamyar, thank you very much. Appreciate you speaking today. And again, want to let people know that if you're interested in having more information about this technology, the multi-touch technology, or the gesture in air technology, please contact the licensing associate in our office who's responsible for that. That's Evan Elder, evan.elder, E-L-D-E-R, at stanford.edu. And we'd be happy to talk with you. This concludes our first in a series of inventor webinars. Thank you for attending today. We will be announcing additional webinars, although you can imagine that it will be across a very broad set of different topics. So typically the announcements will go out to people that we know of who we think would be interested. If you're interested in generally in hearing about all of the inventor webinars, I would also ask you to contact Evan Elder, and we'll put you on a list so that you receive all of these announcements. So again, thanks for your participation.